Today we're gonna start talking about the producer side of the course. So today's lecture and then the two lectures after that is about the supply side. We're gonna start with the production function, and then later on we're gonna look at the firm's cost functions. The cost functions are gonna be linked to the production function, obviously. And then later we talk about the pricing decisions of firms, which obviously is going to build on the cost function. So these three chapters are built on top of each other. They are interlinked, and everything starts with the production function. When you think of a production process, this is roughly a sort of a caricature of a production process. It depends on the output, obviously. I mean, this inputs may change depend on what you're producing, but sort of as a general idea, what you're looking at is a process where you have a bunch of inputs, the chief of which is the labor, the human element, essentially the people that you hire to produce things. And then, a bunch of other things, materials, machinery, electricity. You can include other things like, computers, software, technology, and so forth. And they go into a production process like a black box or a red box, I mean, as it's in here, and then out comes the output, the good and the service that you're producing. So this roughly is the shape that we have when we think about a production process. This is going to be a production function. The production function is going to accept these inputs as ingredients, and the result is going to be the output. This one is the same as before, but it is a tractable model. Tractable in the sense that you express things in a simpler and mathematical way. So the production function, we call it F of KL. K is for capital, L is for labor. So you simplify the ingredients into two pieces. Labor is the chief one, so the human element. And then capital is pretty much everything else, machinery, software, offices, infrastructure, all the things that essentially non-human elements of the production process. You simplify them and you put under an umbrella term called capital K. We're going to use the letter C for costs, so we denote capital with K. So F of KL, F is the production function. So it's going to accept inputs as capital and labor, and it's going to produce the output Q. So when we write down Q is equal to F of KL, we're talking about a production function. Let's have a quick numerical example. Let's say the production function is Q is equal to 2 times K times L. If K is equal to 0 or L is equal to 0, the output is going to be 0. So let's put that in. And then if let's say your capital is equal to 1, if your labor is equal to 1 as well, you're producing well so 2 units. If your labor is equal to 2, 4 units, 6 units, and 8 units. Instead, if your capital is 2 and your labor is 1, so that's basically 2 times 1 times 2 is 4 units there, 8, 12, and 16. And then you get the other ones in the picture. So these are all the possibilities, production possibilities that you can do, that you can have by changing the amount of capital as well as the amount of labor. When it comes to adjusting inputs, capital and labor, it is generally easier to vary labor than capital. As you can see on the slide, increasing the labor requires only a few steps. Just advertise, interview. Just let me quickly just advertise for a position, interview the candidates, and then hire. Depending essentially on the bureaucracy of your company, this could be done rather quickly within a matter of days in some cases. So this allows essentially for a faster response to changing production needs. On the other hand, increasing capital involves a much more complex and time-consuming process. Finding space, sourcing the specific machinery, raising funds, ordering and waiting for delivery, even training labor to use the new equipment, they all add up to significant delays. So this contrast highlights why labor is, often considered a little bit more flexible input, when compared to the capital. And this difference actually is going to be useful when we talk about the short run and the long run. There is going to be a distinction between the short run and the long run. The short run essentially is the time period in which one input, I mean, remember the Q is equal to F of KL, depends on capital and labor. So one of these inputs, capital and labor, is going to be fixed while the other one is variable. As we have seen, it's easier to change labor, to vary labor, and it's more difficult to change capital. So typical approach is that you fix capital at some level K bar, and then you say Q is equal to F of K bar, where this thing is fixed, and L is variable. So in the short run, essentially, capital is going to be fixed and labor is going to be variable. In the long run, in contrary, everything is, all inputs are variable. Let's have a quick example again. You remember the production function that we had before. So let's say in the short run we have 2 units of capital. Well, with the 2 units of capital, essentially your production is no longer the entire sort of possibilities in here. You're stuck essentially with this column there. So the only thing that you can change is labor because your capital is fixed at that. So your production possibilities are nothing but 0, 4, 8, 12, and 16, depending on how many units of labor to hire. Okay, so graphing the short-run production function. Now, this is super easy. All you have to do is just understand that in the short run, your amount of capital is fixed at a certain level, and then just feed that into the production function. If you remember, the function that we had as an example was something like this: Q equals to 2 times K times L. I'm just going to go with this particular example. And our K capital in the short run is 2. So if you substitute 2 in here, so for capital, you just substitute 2. And so the output is just going to be simply 4 times L. And that is what I have in here. Q is equal to 4L. So your short-term production function pretty much depends only on L, simply because K is fixed at 2. And then if you want to plot this thing, I have it in this graph. So you put Q on the vertical axis, L on the horizontal axis, and when you plot Q is equal to 4L, and that's it. That's your production function in the short run when your capital is at level of 2. If your capital is at a level of 3, then you're going to substitute 3 in here. So 2 times 3 is 6. It'll be 6L, and indeed, this is your production function with a level of 3 units of capital. You get the idea. What I want to do in here is to sketch a general short-run production function, general shape for a short-run production function. The previous example was just a numerical example, so this is a little bit more general and reflects the realities of production processes. So it starts at the origin. So it's 0. So labor is on the horizontal axis, and Q output is on the vertical axis. It's got 2 phases. This is the initial phase, where as you're adding labor into your production process, output goes up, and it goes up in an accelerating way. It's kind of like sort of the nice phase of the production process. So it goes up, and it goes up at an increasing rate. Sorry, output increases at an increasing rate. When we are in this initial phase, as each worker is focusing on a specific task, we get more done. This is called the specialization and the division of labor. Everybody is becoming very good at their specific tasks. They are becoming more efficient, and then obviously output is rising very quickly. Specialization and the division of labor phase. But then you reach a certain saturation point. And the second phase starts, which looks like this, called the law of diminishing returns, where output goes up, but it certainly does not accelerate. And indeed, after a certain point, it tapers, and it might even come down. as you add workers. The idea in here is this: if we keep adding more and more workers after this sort of certain point, without increasing other resources, and other resources being capital in here. So, and remember, capital is fixed. So you have a certain amount of machinery, certain amount of capital there, and that does not change. So without increasing the other resources like machinery or space, each new worker is going to add less and less to the overall output. This is the law of diminishing returns. So after a certain point, just adding more labor doesn't boost production. You need capital and you're not doing that. So you just keep adding labor, and this simply is not going to boost production as much because there is only so much they can do with the available resources, with the available amount of capital. So kind of sort of the not so nice phase of the production process called the law of diminishing returns. Technological progress in the short run, how do you sort of account for that, or how do you show that in a graph? So we have our usual graph where the output is in here, labor there, output there. Q is equal to F0. F0 is your initial production function, with a certain amount of capital, and labor is obviously, flexible. So if let's say there is some technological progress, there is a release of AI, and just as an example, and your workers, the people that you hire, they can access that, and they become like all of a sudden a lot more productive than they used to. How do you sort of account for that kind of thing in this graph? Well, the answer is quite simple. You do that. So for any given amount of labor, the production is higher than before. So you kind of, if you just eyeball, I mean, this is supposed to be a straight line. So previously you used to produce this much with this amount of labor. Now you're going to produce that much. Previously you used to produce this much. Now you're going to produce that much. So effectively you shift out the entire production function just like that. And it's going to be F1 of capital and labor. F1 is the production function after the technological progress. The MPL, the marginal product of labor. This is basically the slope of the production function. And the interpretation is quite simple. It's how much extra output we get by increasing labor by 1 unit. So if we increase labor by 1 unit, um, essentially how much output is going to change. Let's say we have L0 unit of labor and they produce Q0 unit of output. So we are here. And I increase my labor by delta L units. So this is the change in the labor. And because of that, the output goes up by delta Q units. So I go from here to there. So what I'm looking at really is the slope of the production function within this interval. And this slope is nothing but, you look at the vertical is delta Q, so that goes to the top. And you look at the horizontal is delta L, that goes to the bottom. And the name of that thing is, the slope essentially is the MPL, the marginal product of the labor, which is delta Q over delta L. The average product of labor, the APL, is even simpler. It states how much output each unit of labor produces on average. So you have Q units of output, you hire L people, Q over L, the total output divided by total number of people you hire is your APL, the average product of labor. In terms of graph, it is the gradient of a straight line from the origin to the total product curve. So you pick a point on the total product curve, let's say that one. So L0 unit of labor producing Q0 unit of output. And then you connect that to the origin. So you look at this straight line connecting the origin to here. The gradient of that line, what is the gradient of that line? Well, the vertical is Q, the vertical distance is Q0, and the horizontal distance is L0. So the vertical is Q, the horizontal is L. and the slope of that straight line is Q over L, which is the APL. So it is indeed the gradient of the straight line from the origin to the total product curve. We want to plot the shape of the marginal product of the labor. So on the top, I have the total output, and in here I have L and L, so I can trace out the same labor. So in the initial phase of specialization, what happens is that the output increases and it sort of accelerates. That means that the marginal product of the next person is higher than the previous one. So each person who is coming in is making even a greater contribution than the previous one. And as a result of that, you see the total product, accelerating, and that means that the marginal product should be sort of increasing. In the second phase, where the law of diminishing returns kicks in, the marginal product is going to start decreasing. Yes, the total output is increasing, fine, but the next person is contributing a little bit less than before. The next person is contributing less than the previous one. The next person is contributing less than the previous one. So the marginal, which is essentially the slope of this thing, is actually decreasing. And then at that particular point, you sort of hit a region where actually the contribution of the next person is even actually less than zero, kind of, harms the production process, and as a result of that, the output actually falls. Total output actually falls. So the marginal product, in fact, is negative there. Next up, we look at the shape of the average product of the labor. Once again, I have the total product there, and I have L and the average product in here, so I'm going to trace out everything in this graph. If you remember, the average product is the slope of this ray that connects the origin and a dot that I choose in here. So in this region, this ray has a sort of, it's kind of a flat ray, so the slope of that thing is the average product. And then if I pick another one, up to this particular point, these rays, they get steeper and steeper. So, I mean, this ray would be even flatter. This one is kind of in the middle. This one is a little bit steeper and so forth. So the slope of these rays, they sort of go up. That means that the average product, which reflects essentially these slopes, is going to go up. But after this certain point, if I pick a point there, this ray in here, this line, is going to have a slope that is going to be less than that one there. So that means that as I sort of start traveling on this total product curve after this particular point, these rays are going to start getting flatter, which means that the average product is going to fall. So the average product curve is going to have this inverted U or a hump shape. Consider three people in here. They have heights, and you look at their average height. So because they have the same exact height, the average height is basically the same height as everybody's. And you bring in the fourth person, the marginal person. If the marginal is above the average, if the marginal person's height is above the average, then is going to bring up the average. If the marginal person has the same height as the average, then, well, the average is just going to stay the same. If the marginal person is shorter than everybody else, if the margin essentially is below the average, then obviously it's going to bring down the average. And this principle is always true. If the margin is above the average goes up. If marginal is below the average stays, below the average decreases. And in a knife edge situation where the marginal is exactly equal to the average, then average stays the same. Now let me put these two shapes together, the MPLs and the APLs. I know from the previous slides they are both hump-shaped, inverted U shapes, but how are they exactly sort of related to each other? Well, first principle is that the marginal is sharper. So marginal goes up fast, comes down fast. Whereas the MPL, the APL, the average product, is kind of slower. So it goes up slowly and then comes down slowly. Okay, um, that's one principle. The other one is this: the marginal cuts the APL at the point where the APL is at its maximum. This is the point where the average, the black curve, is at its maximum, and the green one, the marginal, cuts it right at that point. To the left of it, the green one is on top of the black one. The marginal is above the average, and that reflects the idea that whenever the marginal is above the average, it brings up the average. Remember that height example. To the right of it, the marginal, the green one, is below the average, the black one. And again, the same principle. If the marginal is below the average, it brings down the average. And exactly at that particular point, they are equal to each other. So marginal is equal to the average right at one point. It's a knife edge situation. In the long run, both capital and labor are flexible. So the way to represent the output is this. You put labor on the horizontal, capital on the vertical axis, and then you draw the so-called isoquant curve. An isoquant curve is basically a curve that shows the combinations of capital and labor, all input combinations, that yield the same output, Q0. So along this curve, the output is always the same, Q0 units. Pick this point here. This is a very labor-intensive production process. You have a lot of labor, very few units of capital, and you produce Q0 unit of output. It's quite labor-intensive production. The other extreme, this is very capital-intensive, so you have a lot of capital, very few units of labor there, but you still produce Q0 units. It's the isoquant, it's the same quantity. And you can sort of have somewhere in between. I mean, you have intermediate amount of capital, intermediate amount of labor there. So all these possibilities essentially are there. That kind of represents the long run production process. And the way to sort of get this curve is basically you set the production function f of kl equal to some q0. You can pick what q0 is. I mean, that is up to you. And then you solve for k because k is on the vertical axis, and then you just plot it. And it has this curve obviously has I mean, roughly the same interpretation as the indifference curve that we had seen initially. Anything above that curve has higher output than Q0. Anything below that curve has output lower than Q0. So you can imagine the entire space being filled with these curves like that. So that would be associated with a higher amount of output than Q0, and this one would be associated with a production level that is lower than Q0. Next, I want to sort of get a sense of the slope of this isoquant curve. If you remember, like the isoquant kind of sort of looks like this. So I'd like to sort of have an idea of the rate of change along this curve. And in order to do that, we're going to need both the marginal product of the labor. We have introduced this already. So MPL is the sort of how much each extra unit of labor creates in terms of output. So you sort of hire the next person, what is their productivity? The marginal product of labor is, we've done that. So we need another notion, which is the marginal product of capital. It's the same exact thing, but obviously in terms of capital. So each extra unit of capital creates MPK, marginal product of capital units of output. So how much the sort of last unit of capital contributes towards your production. Same exact thing as MPL, but interpreted in terms of capital. I'm looking at this isoquant curve, starting from point X, and I move towards point Y. Point X is more labor intensive. There is more labor and less capital in here, whereas point Y is more has less labor and more capital. It's more capital intensive production. So basically, fire, let's say, delta L units of labor, and instead I acquire delta K units of capital, and still am on the same isoquant, meaning that my production level is the same as before. So output does not change. I just basically change the composition of capital and labor. And by looking at these things, I want to basically get a sense of the rate of change, the slope of this isoquant curve. Okay, so moving from X to Y, there is less labor obviously involved. So because of the less labor, because of this delta L, and it's actually negative obviously, because change is negative in here, output is going to decrease. By how much? Well, MPL is how much each unit was producing, and I lay out, I fire essentially delta L labor. So delta L times MPL would be the loss in quantity because of the decreasing labor. Okay, now I increase my capital, so I acquire delta K units of capital. So this is the change in capital, the extra capital that I bring in, and each one of them is producing MPK units. So this is the marginal product of capital. Multiply them both, and this is going to be the increase in production due to the new acquisition of capital. Both input combinations, they produce the same output. I'm on the same isoquant curve, so the total change should be zero. So therefore, MPL times delta L, the loss in quantity because of the loss of labor. Notice this delta L is negative in here, so you don't need to put a minus there because delta is just negative. Plus MPK times delta K. This is the change because of the capital. So this total change has to be equal to zero. All right, so I have that equation. Now, if you look at the slope of this curve, look at this triangle. The slope essentially would be what? The horizontal divided by the vertical divided by the horizontal. Vertical would be delta K, horizontal would be delta L. So the slope essentially would be delta K over delta L. From here, you can maybe pause the video in here. So you can sort of use this equation to note that delta K over delta L is going to be exactly equal to minus MPL over MPK, simply because of this equation. It's just a matter of, quick algebra. Send MPK delta K to the other side, divide both sides by MPK, and you will basically get that equation. And so that is the slope of the isoquant curve, the gradient of the isoquant curve. It would be the MPL over MPK, the marginal product of labor over the marginal product of the capital. Notice it's minus because this thing is downward sloping. And this has a name. It's called the marginal rate of technical substitution, MRTS. And the interpretation is quite simple. How much capital can be substituted for 1 unit of labor without affecting the total output? So you stay on the same isoquant, so without affecting the total output. The rate of substitution essentially between labor and capital so that you sort of stay on the same production levels. So MRTS, the margin rate of technical substitution, is equal to MPL over MPK. Here we are not interested really in the minus sign, so it's the absolute value. Just pay attention to that. The returns to scale, this is an important property of the production function, and there are basically, the idea is very simple. So if you double all the inputs, if you double all your capital and labor, what's going to happen to the output? Let's say you initially have K units of capital, L units of labor, and you produce Q units of output with that. Okay. Suppose you double all your inputs, so it becomes 2K, 2L. Question is this going to become 2Q more than 2Q or less than 2Q? If indeed the output doubles as you double your inputs, you'll be talking about constant returns to scale. If output more than doubles, then we're talking about increasing returns to scale. And then finally, if output less than doubles, then we're talking about decreasing returns to scale. Double is just an example. I mean, it could be any scaling factor in here, S. So if S is equal to 2, we are doubling. If S is equal to 3, we are, tripling. If S is equal to 1.5, it's, 50% increase and so forth. So essentially, if the output increases by exactly the scaling factor, we're talking about the constant returns to scale. If output increases more than the scaling factor, then increasing returns to scale. And then if the output goes up less than the scaling factor, then decreasing returns to scale. Here's a quick example. So the production function is equal to k times L. And let's say I go with S is equal to 2. So, I mean, if you substitute essentially Sk and Sl there, I basically apply the formula there. So for K, I have Sk. For L, I have Sl. So this becomes S squared times KL. So if S is equal to 2, then that will become basically 4 times KL. So I double the inputs, capital and labor, the output quadruples. And so what we are talking about in here is then increasing returns to scale. So this production function indeed has increasing returns to scale.